for the first one, well, that was pretty easy from the last exercise class.
Yes.
We knew that there were 5 classes. And then we know that the number of irreducible representations is the same number as that of the classes.
Yes.
Or number of classes. So there's 5 irreducible representations. And we have 8 elements. So the sum of the dimensions squared for each representation must equal 8. So we can write it up like 1, 1, 1, 1, 2.
Yeah. So I guess this is the only possible solutions.
Sorry?
It's the only possible solution, right? Can you get other solutions? I don't think so. I think it is the only possibility.
Yeah.
Let's see. Can I have 1, 1? No. If I have 2, then it will be will be finished. Yeah. So then it should be. Yeah. I think that's the only possible solution. So there is quite a lot of restrictions in this rule. It eliminates lots of possibilities. Yeah. Okay. Good.
For 1b, then I set up the character table, and initially I only had the first row and the first column.
Yeah.
So the first column is just the dimensions, and the row is just the
identity.
Yeah, identity. So I've written down here how I found all the characters inside, and I know that the square of all the classes has to be of the unity class, unit element.
Okay.
So from the multiplication table, I think.
Okay, so you're using the fact that the square of the elements in the class is equal to the unit element.
So
is that
sorry, isn't C double dashed? C double dashed, isn't that?
So what is C double dash now?
I wasn't sure what like the formalism was yet, but so yeah, the CA, CT, and then CC with 1 dash is C2.
Yeah, okay. For the C2, CC double dashed, so that's C1 and C3.
Yes.
That squared would be C2, isn't it?
Sorry?
So
that square would be C2, right?
Oh, okay.
C1 squared is C2.
Yeah. I mean, you have a rotation by 120, right? Because
90 degrees. Right?
Let me see.
C double dash squared should indeed be just the class of unit element in C2, because you have the multiplication first C3 times C1, which is obviously unity, but you also have C1 times C1, which is C2.
Yeah, but the thing is, the identity element and C2 are 2 different classes, right? So I agree with the table. The table is the same that I have.
So the C3 is a rotation by 3 pi upon 2, right?
Yeah.
So if I multiply it by twice, that will be 3 pi. Okay.
Yeah, I guess. Well, some from the class will give the unit element, but yeah, some of them will give C2.
But yeah, but that is not equal to unit element, right?
No.
Because C3 gives you C2.
So then there's probably, something not right with the arguments I made.
I did this in a different way, going back to the last exercise when we set up the factor group tables.
Yes.
And we will get this same table doing that, but then we instead use what the multiplications become in the factor group multiplication tables to get this same result in the end.
Do you want to show that? I would like to see how to do it with the factor groups. Because
I don't actually have it properly written out. If someone has the factor groups from the last exercise written out, we could probably look at those instead, I think.
Okay. Anybody has the solution for the factor group I mean, I have it here in my solution, so it would be better if one of you could present it. No, so let's see. Okay, so shall I then share a screen with you? Okay, maybe you can take off your screen. Yes. And let me see, what do I have to do here? The whiteboard. Yeah, it works. Okay, so let's work out the character table. So I think there are, let's see, there are 3 factor groups, yes. So there is several invariant subgroups. So for example, in my solution here, I have E and C2. So let me write down the classes first. So the classes is E and then CA. So that is the AX and AY. And then I have C2, which is just C2. This is the capital C here. This is the small c. And then I have the C4, which is the C1 and C3. And then the CD is D1 and D2. So these are the 1, 2, 3, 4, 5 classes. Yes, like Nicolene has said before. So this gives me a invariant subgroup, like for example, this one here. So the unit elements C2 and C4, that forms an invariant subgroup. Is that clear? Yeah. So if you have something that is not clear, just raise your hands or just say something. Yes. So this is an invariant subgroup here. So then we can form a factor group from this, which is just S1 itself. And I think we can take any of this G, because there's only, we can take any of the G outside the S1, any group element. So this would give me then CA and CD. Okay, so you take any of a group element outside S1 and multiply it by S1, then you get this coset. Okay, yeah, good. So now we can construct the factor group, the character table or the multiplication table of the factor group. So this is just S and GS, S1 here if you like. It's very simple because it is just it just has two elements. So I can call it, what do I call this here? Let me look. I call it A plus, A minus. So 1, 1, because it's two elements. So the factor group has only two elements, S1 and GS1. So then the dimension can only be 1, yes, for both representations. And this then must be equal to -1 from the orthogonality of the characters. Yeah. So, so now comes the important steps, is that we can use this character table or the representation for the factor group as the representations for the original group, yes, because of the homomorphism. You remember that you can associate the group S1, the element S1 with the bunch of element E, C2, and C4 here. And then you have GS1, which you can associate with the other one, the CA and the CD. These are the classes. So, because of this homomorphism, I can use the representation for the factor group as representations of the original group. So this means that I could, for example, so the first one is not interesting because that just gives me the identity representation. Yes, because this means that all elements is represented by 1. So it's not interesting. We already know that. Okay. So what's interesting is this one here. We can make use of that to replace or represent. Let me see. So let's start with this one here. Yeah. So I represent EC2 and EC4. So that's the S1 by 1. So I'm looking at this one here. And then I can take the CA and CD and represent it with -1 because these groups, these elements here, is associated with GS1. And GS1 is represented by -1. So we can also then use the same representation for these elements. Is that clear? Because of this homomorphism, yes? So that's an important point. Okay. So is there any question about that?
Yeah, I have a question. So where does that -1 go in the original character table? Now that you've deduced that CACD is -1.
Yeah, that's a good question. So now I can, okay, I have to, maybe I can create another one here. Yeah. So now I have the character table like this. I have 5. 1, 2, 3, 4, 5. 1, 2, 3. I need more here. 4, 5, like this. Yes. So now I have. Let me write down the classes first. C2. So this may not be in the same order as Nicolene wrote, but doesn't matter. These are just my order. C2 CD like this. Yeah. And then I have, I think it's called A1. So I'm following the convention, I think, in the convention for labeling the irreducible representations here. But you can call it any way you like. You can call it T1, T2, T3, and so on. Yes. So this is 1, 1, 1, 1, 1, and then we know 1, 1, 1, 2. Yes. So now we can use this homomorphism. So we had before, let me see, can we go back to the original one? Yes. So we see that we represent the elements belonging to CA and CD by -1. Okay. So then in this character table, we look at CA and CD. So these two here, which we replace with -1. Okay, so then it becomes -1, -1. Because we are looking at the one-dimensional representation. So I'm looking at this one here. I could have chosen these two, of course, B1 and B2, because they are also one-dimensional. But then it's just a matter of labeling the representation. Yeah. So you can choose any of these one-dimensional representation. Okay, and the other one is just 1, 1. Because we replace, we look at this one here, the C2, C4 is, of course, the unit element is replaced by 1. Okay, so now if I look at this one here, C2 and C4, this one here, this 2 is replaced by 1. Yeah. Okay, so we can go on and look at, let me write down here. So I have EC2C4, C2CA. So this is the other invariant subgroup. So let me call it this S2. It also forms an invariant subgroup if you work out. So let's see, C2 and CA. C2 is supposed to be, what is it? So C2 is a rotation by pi around the z-axis. And CA is, of course, the AX and AY. So they form a subgroup. Yeah, and it's also invariant because you can tell from the fact that they consist wholly of classes. Yeah, so this is also invariant subgroup. Okay, so this I can associate. Okay, so let me look at the other elements. So now if we look at the GS2, so that becomes, I think, C4 and CD. Yes. So this is the coset. If I take any of element of G, then I get this. So this G can be anything outside S2. It doesn't matter which element, as long as it is outside S2. Well, obviously, if you take a G within S2, then you get back S2, yes, because it's a group, because it's a subgroup. So now I can also associate this with 1, because this is the unit element, and this one with -1. Okay, so I can just use that. What do I have here? So now C2 is 1, and the CA is also 1. Yes, because C2 and CA is now associated with 1. So I fill this element here, C2 and CA with 1. I fill that in, and then the C4, CD is -1. So that is -1 and -1. So is that clear, or is there any question about this? Okay, and we can do same thing for the, I think there is another invariant subgroup. So let me call that this S3. So that is E, C2, and CD. So this also forms an invariant subgroup. Yeah. And GS3 then would be just the rest, would be CA and C4. Like that. So we do the same. So we associate this S3 with 1 because that's the unit element of the factor group. And this is with -1. So we can just fill in the rows here for B2 for this representation. So we have C2 and CD. So now it is 1 here and 1 here. And CA and C4 becomes -1, -1, like this. So the rest can be easily obtained using the orthogonality between the characters. So we use the orthogonality between the characters. So then this must be equal to -2 here. Because if I look at these two columns and form a dot product, we have 1 plus 1 plus 1 plus 1, which is 4. So that then must be subtracted, here -4, 0. Okay, and the same here. So then this has to be, well, we have to use also, let me see, so we can, yeah, so we can multiply this 2 here. So then this must be equal to 0, because this is 1 plus 1, which is 2, and then -1 -1. So it's 0. So then it has to be 0. And the same here, it's going to be 0 and 0. So we have constructed the character table.
Could I ask you about the labeling of the representations?
Yes.
You said there was a convention. I haven't heard about this before.
Yeah, this is not so important for our purpose. I mean, I don't remember myself the conventions, but I think A usually refers to a one-dimensional representation. So it has to do with the dimension of the representation.
Okay.
Okay, and E is 2, I think.
Is it Mulliken convention?
Sorry?
Is this Mulliken convention?
Yeah, I don't know. I don't know what the name of this convention. But there are different kinds of conventions, I think, depending on whether you are doing chemistry or you're doing solid state physics. So what's important, I mean, it's just a label, yeah? So you just have to, it's not so crucial.
Right.
Just to know that when you see a label like this, it might have some meaning. Yeah.
I was just wondering, because you said A refers to a one-dimensional representation.
Yes.
And E to a two-dimensional. So is there a reason for naming those B instead of A?
Oh, I don't know. I have no idea. I don't know. So many of these labels often come from the German words. So usually people use D for the representation instead of T. I think the T maybe is the English version. So if you look at some old books, sometimes they use D for the German word. It's from the German word of representation. Yes, I think it's called Darstellung or something. So yeah, but anyway, these are just not so important, I think, for our purpose. So as I mentioned before, all these character tables you can find actually at the back of group theory books usually. So it's all listed because there's just a finite number of them, so we can make use of that. But I think we should know how this is constructed. Okay. Is there any? Oh, sorry. Is there any questions?
I have a question. This when you put like this from this factor group.
Yeah.
Character table. You took the 1 and -1, but could you also take a 1 and 1? I mean.
Yeah. But then it just gives you this identity representation. You see.
Yeah.
Yeah, because you represent each element by 1.
Yeah.
Yes.
Yeah,
So, but then it becomes identity representation. So we don't use that because we know already.
Yeah.
Yeah.
Okay. Yeah.
So I mean, there are only 2 possibilities in this case, right? There's the either use the 1, 1 or the 1 minus 1. If you look at this thing here, the multiplication table, there's only 1, 1 or 1 minus 1. Yes, these are the 2 irreducible representations of the factor group. So the 1, 1 then gives you the identity representation. If we use this and use the homomorphism, then all the S elements will be replaced by 1. Then you just get the identity representation.
Yeah.
So it's not interesting because we already know.
Okay. But what if we have a bigger factor group table? Then we have a lot of options to.
Yeah. Then you have more options, of course. You can have for example, 3 by 3. Yeah.
Okay.
That's true. Okay, so this is one way of constructing the character table. So shall we continue with the next question here? So I think the next one, unless you have some more questions about this part here. So if you don't have any more questions, we can maybe continue to the third part of the problem 1. What is it about? So determine the coefficients in the class multiplication products. Yes, anybody would like to try?
I tried to use the 2.10 equation in the lecture notes.
So let me switch off that.
I found a really big system of equation, and
I think you can just. Okay, I think you can just do this by kind of by inspection. You just multiply the classes. So I mean, if you take, for example, class CA and CD, so let me. So, is there anybody who would like to try this?
I think in our group we weren't completely sure what this M kind of.
Okay, so let's do this together then. Yep, just a whiteboard. So the general thing is that you have 2 classes, CI, CJ, yes, and we worked out in the lecture that this can be expanded in terms of linear combinations of other classes. Something like this, I think. Yeah. So if you multiply 2 classes, then the resulting elements can be regrouped into a series of classes. So let's take an example. I think it makes it clear. So if I multiply, let's say, CA, CD, so these are the classes CA and CD. So what are these? So these are the element AX, AX and AY, that's CA, and the CD is the D1, D2, like this. Yes. So now I just multiply this out. So I look at the multiplication table that we did last time, I think. If you look it up, the multiplication table, then you find, well, let's multiply this out first. So I have AX dy, and then I have AX d2. So I have 4 elements then, and AY d1 and AY d2. Yeah, I just multiply this out. So what is AX d1? So I will look it up in my multiplication table. Where is it? Where is my multiplication table? See, I have it somewhere. Yes, I have it here. So if I look at the multiplication table, then we find that AX times D1 is equal to C3, I think. Yes. So this is equal to C3. And AX times D2 gives me C1. Is that correct? To give me C1, yes. And then AY times D1 also give me C1. Yes. So give me C1 like this. And AY times D2 gives me C3. Yeah. So this is just looking at the multiplication table. So from multiplication table. Straightforward. Well, you see that C1 and C3, I think, forms a class. Yes, so this is the C4 class. So this is also C4. So then it becomes 2C4. Yes, so this coefficient, it turns out to be just one class. There's only one class here. But in principle, it could be some other classes. Yes. If you multiply the other classes. So this is the coefficient, the Mij here. So I can do the same thing for the other classes. So if we look at table, generate table. So there are 5 classes. So this is actually quite straightforward, I think. It's a matter of multiplying things out and just work out what the classes are. 1, 2, 3, 4, 5, like this. So I have E, C2, C4, CA, and CD. And then I have E, C2, C4, CA, and CD. Like this. So what do I have here? So we multiply CA and CD. So we multiply this one and that one, and we find that it's equal to 2C4. And we can do the same, yes. I think we don't have to do this. Yeah, that's going to take a long time. It's quite straightforward. So this becomes just E times C2. So let's see, this should be then SE, C2, C4, CA, CD, of course, because it's just E, unit element. And then we have C2, if you multiply C2 and C2, then you will find that it's equal to E plus C2. You can check that. This is what I have in my solution here. So I might make a mistake, of course. You can check. So you multiply C2 and C4, you get C4.
Freddy,
Then this gives me, yes.
I was just wondering, how would C2 and C2 give E plus C2? Like, I could see that for C4, CA, and CD, but not for C2. Because if I'm not mistaken, C2 is just one element, right? If we have one element times one element, we would
Yeah,
get
you're right.
just
So,
one.
so it could be two elements here. Yes, it could be 2E plus C2. Let me check here. I just have the results. I might have made a mistake in the. Okay, so let's work it out. I think you're right there, because just by counting the number it cannot be right? So C2 is what now? C2 is.
It's just the element C2, so the only element
no,
in
it's
the
element
multiplication.
C2. I see.
Yeah.
So then it's okay. So then it's okay, right? Because no, it cannot be, because there's only.
It should
one
just be
element.
unity.
I think this will be just unity. Yes. Why do I have plus C2 there? I think okay, that's a good point. Yes, C2 is actually only one element. C2 is only one element, so that corresponds to what is it? Rotation around pi, by pi around the z-axis. Yes. So C2 then of course give you E. Yeah. So that was a mistake. That's good. Thank you. So this one here is a mistake. This one.
Could I also ask you about the sort of the procedure we're following here? Because in the lecture notes, there is an equation, I think 2.10 or something like this, that talks about this table, constructing this table, finding these coefficients MI, JK, from the characters of the different classes.
Yes.
And I would have, I mean, presumably we have a character table, so if we ever,
that
equation was ever useful, then it should be useful here.
Yeah, you can also use the character table. It's kind of more direct, yes, because it's such a small group.
Right, but I think because I mean, in this case, we're fortunate that there's only two elements in each class, one or two elements in each class.
Yes.
Yeah.
So in general,
for larger classes, this wouldn't work.
That's right. So if you have, in general, you would like to use these formulas in the book, in the lecture notes. So you use the kind of orthogonality relation that gives you these coefficients.
And then you have some sort of a system of equations.
Yeah.
So, all right, that makes sense.
Yeah, that's right. So I guess the idea of this exercise is just to see that you indeed, when you multiply two classes, you can see explicitly that it does give you a linear combination of the other classes. But in general, you would use this formula. So that can also be used to help you construct the character table. It's not so used very much though, but it's another information you can use to construct the character table. Yes, that's a good point. Okay, so let me fill up this thing. So I don't make a mistake now. C2, C4. Let's see, C2, C4, give me C4, and then this is CA, I think. Oops. And CD. So we only need to construct half of it, yes, because the correct table of the multiplication table of the classes is symmetric. So I have C4, C2, C4, C4. That gives me 2E plus 2C2. Then 2CD and 2CA. And if I continue, I think I get 2E plus 2C2 and 2E plus 2C2. If I have done the calculations correctly. You can check.
See, sometimes I ask you like questions on linear algebra, and I'm like, she must know this because she's taken it just recently.
Okay.
I haven't covered this. Maybe.
So, trick. Symmetric.
That's the only time we
See
to find the inverse of a matrix.
Mm-hmm. Okay, so what do I have here? So is there any other questions about this part?
I have a question.
Yeah.
So the coefficient is that just like 2, 1 or 2, or then what do you do when there's a sum of when the result is from two different classes?
Yes, so that is what we have, for example, here.
I don't think that. Yeah.
Oh, that was not good. That was erased. For example, if you take CA times CA, yes. So that, according to my table, this is equal to 2E plus 2C2. These are the coefficients.
So is the coefficient just still 2?
Well, I mean the general formula is like this. Yes, we have sum over.
Also, then you separate them depending on whether they give the unit element or the C2.
Yeah. So this E forms a class, right? This is another class. So I have, in general, I will have something like this.
Right, that makes sense.
Yeah.
Right.
We're actually summing over all the classes, so we should
summing
note that
over
all the other coefficients are just 0 in this case. So
yes.
we still keep that in mind.
Yes. So it just means that the other don't have. I mean, it's not part of CA times CA. Yes. So only these two classes appear when you multiply the elements of CA by themselves. Yeah. Okay. Any question about this part? Or other questions about the courses, other points in the courses which are not clear. Okay, maybe we can have a little break then. What time is it now? It is 11. Oh, well, no, that's a good time. Maybe we can continue at 11:15, unless you have some other questions. Okay, so, yes. Sorry, you want to say something?
I just said see you at 15. 11:15.
11:15, yes.
Yeah. See you.
Very good, thanks.
I have a quick question about the assignment.
Yes.
Is that the exam or is it some other assignment?
I'm sorry?
The assignment that you uploaded earlier this week, is that the exam or is it some other assignment?
Okay, so we have this home assignment. So that you have two sets of problems, I think. So one for the discrete groups and one later for the continuous groups. Yes. So the home assignment is the one that has been uploaded into the website. So later there will be an oral exam for 30 minutes each.
Okay.
Yeah.
So then this one is the written exam for your part of the course.
Yeah, you can think of it like that if you like. It's more like home assignment. I mean, you have like 2 weeks to do this. So you can do it at home.
Okay.
Yeah.
I have a question about the oral exam. Do we have any preparatory questions for those? My immediate guess is that those are the review questions in the lecture notes, but I would just like to make sure.
Yeah, so those are exactly what the purpose of this summary of questions at the end of each chapter I have in the notes. So if you just go through those questions, then I think that should be sufficient.
If we have questions about those, should we just send you an email or what would you?
You can send me an email, yeah, if you have questions about those questions. I think they are all in the notes. I think the answers, but maybe some are not so clear. So yeah, you can ask, of course. So typically for the oral exam, I will go through the home assignments just to see that you have done it correctly, and if there are some mistakes, we can discuss. And then in the remaining time, I will pick up some questions from this list of questions I have in the notes. Yeah. I mean, some of these are very easy, so I will probably not ask such simple questions. Some definitions and things like this are not so interesting. So, yeah. So if you know how to answer those questions, and I think you should be in good shape, I would say. It's nothing very difficult. I mean, the purpose of the exam is not to test how clever you are. I mean, it's just more of testing that you understand the courses. Yeah. So,
I have one question. But these character tables, are these unique?
Yeah, it's unique.
Okay.
The character tables are unique, yeah.
Because I was thinking if you have the higher factor group, then I feel like there could be some options how to construct it. It should still be like satisfy the orthogonalities and so on. I think you could like flip some signs somewhere or like.
Yeah, but I mean, you will probably not find a higher order factor group for this case. You're talking about the D4 group. The
yeah,
group,
but I was thinking about the bigger ones.
Well, yes. I mean, you can have bigger factor groups, but it will give you a unique solution.
Okay.
So the character tables are unique. Yes. So in the beginning, like if you recall that you have representations, and there are several ways of characterizing this representation. Yes. So one way would be to calculate the eigenvalues, for example. Okay. But this is very awkward to do, yes, because you have to diagonalize the matrix. So the character tables is probably the simplest way of characterizing an irreducible representation.
Okay.
It's unique, yeah. So if you have two different groups, it is almost like definition. I mean, if you have two groups which have different character tables, then they are by definition different. Because if you have two groups which have the same character table, well, then they're equivalent. Yeah. They're isomorphic to each other.
Yeah.
So for example, we have this D3 group, this equilateral triangle. So that is isomorphic to the S3 group, yeah. Okay. The permutation group. So they both have, of course, the same character table, the same multiplication table. Yeah.
Okay.
Yeah. So that's for the discrete. Yes.
Because, so if I understand it correctly, the representation, like there's supposed to be a homomorphism from the group elements or from the group to the representation.
Mm-hmm. For the factor group, you mean?
No, from the group. Like in general, when you define the representation, mm-hmm. you define a representation such that you can make a homomorphism from the group to the representation.
So you mean isomorphism?
Isn't it homomorphism?
Homomorphism means that you represent several elements by same.
Oh, okay. Sorry, yeah. A homomorphism from the representation to, because I'm thinking like when you have any group mapped to the trivial representation, mm-hmm. that's not an isomorphism, right? That couldn't be.
It is an isomorphism.
It is isomorphism, yeah.
But the identities aren't unique. That's the point.
Oh, okay. But it's still an isomorphism.
Yeah, it is isomorphism. Yes.
I see. Okay, that makes sense.
So there is a one-to-one mapping between the representation and the group element. Yeah. Whereas homomorphism means that you have one representation for many elements.
Yeah. Okay.
So the identity representation, it looks like a homomorphism because you have the same representations, one for all elements, but it's a one-to-one. Yeah?
Right.
So each element is represented by one.
Yeah, each group element is represented by one matrix. Exactly.
Yes.
Okay. Yeah.
Yes.
When we talk about the identity representation, are all those identities different in some way, or?
What do you mean? I mean, you have identity representation just means that each element is represented by a number one.
Right, but I think someone here did say that there's some difference between those identities in some way. Mm-hmm. I mean, that's the reason why it's not homomorphism, right?
You mean let me see if I understand what you mean there. I mean, you can probably also think of it as a kind of trivial homomorphism. You have just one element, one, and then you map it to all the elements in the group. Is that what you mean?
Yeah, that's what.
Yeah. Yeah, you can think of it like that if you like.
Okay.
Yeah. It's kind of trivial, yes, because you have kind of unit element. Of course, you have a group with one element. So strictly speaking, it forms a group if you have just one element. Yes. So yeah, so you can think of it as a homomorphism, but kind of the other way around. Yes, from the representation to the original groups. Is that Okay.
Yeah, that's what I was thinking about. Like if it's a homomorphism from that one representation to the different group elements there. But
yeah, I think you can also think of it like that. Yes, but I would rather think of it as an usual isomorphism in the element, and each element of the group is assigned representation 1.
I think it's just slightly difficult to understand like how all of them have the same representation, but I guess it's just because it's an unfaithful representation.
Yes. So if the representations are the same, if the representations are all different, then they are faithful. If not, then they're not faithful. Yeah. Okay. So maybe we can continue with the next problem. I think we can skip problem 2 because I think it's quite straightforward. So maybe we should do number 3. There's a lot of algebra number 3. So anybody from the 4th group would like to try?
Yep.
Yeah, good.
Yep. I can.
Share.
Yeah, I'll show my go at it.
Okay.
All right. So let's see where it's. Okay. No. Wow. Okay.
Very good.
All right. Yeah.
Can you make it bigger?
Yeah, I think I shared the wrong thing.
Yeah.
There we go. I think. You like that?
Yes.
And then. Okay.
Yeah, good.
Yeah. All right. Okay. So, we want to prove this specific relation here.
So can I just comment? Can I just comment? Yeah. So we recall that we have the orthogonality theorem. Yes. So which you have here. And then we have the first orthogonality relations for the characters, yes, and the second orthogonality relations, yes. So the first orthogonality relation and the second one, they're kind of complementary, yes, because one is with respect to the representations and the other one with respect to the classes, yeah. So this one here is also similar to this. So you have the orthogonality theorem, and this one is a kind of complementary version of the orthogonality theorem, but with respect to the group elements. Yes. So that's the kind of reason for this exercise here. Quick, let's please continue.
All right. Okay, so from the orthogonality I will give you this is here as a heterotopology.
Yes.
So we have the same J, then we can say that the should be 1.
What do you mean by this thing here?
Well, then should just be the inverse of this.
I see.
And then that should be 1.
So there is some J.
Yeah.
Okay.
So in the case you just have that J times UTG, then it's simply sum over IJ, which would simply, when we do that, it would simply give dimensions L alpha. So then we simply get out sum alpha over alpha times alpha, which from our results, which is that alpha squared is H. So in the case G prime equals G, we have that is equal to H. So then if G prime is not equal to G, then this is a formula vectors, then these two would not be the same anymore. And so if they're orthogonal, then they should be 0.
Let's let's see. This. So maybe you could repeat it and restart it and try to follow the reason.
Yeah, that's right. So set over orthogonal vectors. We have that large orthogonal vectors. This simply inverse this, which is equal to 1. So if G equals G, you have the same thing here. So then we do some number ij, which is give us the dimension, which is going to get the dimension times the square, which gives us h.
Yes.
Then these are a set of orthogonal vectors, and we have a representation of one element, G, the representation of another element, G prime, which is not equal to G. This has to be a different vector. So if they're orthogonal, a set of orthogonal vectors, this product should be 0.
Yes, but that's what you want to show. I mean,
okay.
Yeah. Let me see if I can actually conclude with like this.
Okay.
You may be right. I'm not sure if I understood completely. I mean, what we know is that we have this set of vectors labeled by alpha ij, which are orthogonal.
Yeah.
And you can think of the G as kind of the basis vectors. But I think we want to show from the fact that these vectors are independent. We have an independent, not independent, let's get it. Each independent vectors labeled by alpha ij. That from that, we want to show that the G are different than the sum of the labels give us this delta or delta.
Okay.
But maybe I missed something.
No. Yeah, I just think I skipped over that.
Okay. So I just have any comment about this.
We also tried to do the first one in our group. Well, we weren't able to show it without using one of the other theorems that follow along the orthogonality theorem.
Okay.
So it sort of reduced to what we needed this theorem to show it.
Okay.
But I guess that's the exercise, right? Because we're supposed to show it just by so.
It's very fine, if you like. Okay. So anybody would like, anybody else would like to try this or comments? I can try to explain what I think of this problem.
Yeah, I can stop.
Let's see. So actually, it's rather similar to what we did in the class for the variety of the characters. Yes. So we say that we can construct a vector V from this independent vectors. So let's see, we have some coefficients ij. So I'll call I and j labels the independent vectors like this. So we can remove the g first. Like yes, we know this that we can construct an arbitrary vector in the h-dimensional space of the group elements. So I can also put a g on because there's just a projection on the g-axis. So now from the orthogonality theorem, we can work out these coefficients. So this is from the orthogonality theorem. We can get this vector in alpha h sum over, I call it g prime. Have a vector g prime. Yes. So basically, I multiply. I can choose a different label. I can multiply this both sides by, let's say, beta. Okay, like this. And then I use the orthogonality theorem. Yes. For this thing. Maybe I sum over the g's, and this is what I get. Is that clear? Yeah. Okay. So now I can then use this result here. Then I can write. So this is a bit like verifying that these vectors are really orthogonal with respect to their group elements. G prime here. Then I have the alpha star ij g prime ij g. Yes. So I'm substituting this coefficient in here. So this whole thing here. That's my C alpha ij. And then we can rearrange this so that we can get sum over g prime, vg prime, and then I have sum over alpha ij, h, minus the g prime. Yep, I'm just rewriting this equation here. So that because this vector is arbitrary, then this should be 0. Just what we want to show or verify. So this is kind of the complementary version of the orthogonality theorem. So in the case of the characters, we have these two relationships, the first orthogonality relationships and the second orthogonality relationships. And this is a kind of more detailed version of those orthogonality relations for the representations. So instead of representation in class. Here we work with the representations and the group elements. It's a more detailed relationship. So is this all right, everybody? Yes, and I can continue then.
All right.
Yep.
Okay.
So you want to continue? Next one. Yeah.
All right. Let's see. I'll give it a go.
Yeah, I have to think a bit about what you said because it's not immediately obvious.
No. I think no. You're completely right. I messed up there. All right. All right. Let's try this one. Okay. So we have the rewrites.
Yes, that's the definition of trace.
So then from what we got here, we set j to I.
Yes.
Have the command like this. Something like I.
Yes.
This. There's different elements and also different classes. It's kind of the same class. So I call them CCL. We have a refactoring K. Well, then I'm claiming if we write it like this. I think.
Let's see. Okay. You have some number from X. Storage G. Yes. Yes. Oh, wait a second. Oh. So how do you go from? You have this equation. It's difficult to point. You have this equation of how do you go from the left hand side to that one?
Okay, you rewrite this one using like the weighting factor in terms of class or.
But the G and G prime can be anything. Right? They are arbitrary.
Yeah.
So what do we mean here by? So you're saying that I can replace G by the class to which it belongs.
Yeah.
But why do you have this NK then?
But don't you have to introduce the weight factor, like when you introduce the classes?
But I mean, here you have just one element G and G prime.
Yeah.
So I would have thought it would be a bit too much, no? Because you multiply by NK.
Okay.
Yeah, so that one.
Yeah, okay. Wow, yeah. You want to show the correct derivative?
Okay, I can continue, yes. Let's see what I have here. From A. So we have a sum over alpha ij, the alpha star, ijt, the alpha ij, g prime, equal to h, g prime. That's what we just shown. So now I can do the summation. I think this is probably what you would like to do. You sum this over G belonging to a certain class, let's say CK, and sum over G prime belonging to certain class CL, let's say. Yeah, so you do the same here. You do the sum G, CK, and G prime CL like that. So what do we have here is that we have H times the number of class times delta KL. So we have this thing here gives us what do I have here? Wait a second. Okay, so we still over the G and G prime. And then I have. Okay, so what I'm trying to say here is that if the G and the G prime belong to two different classes, then of course they will be 0. Yes. Because you remember that group element cannot belong to more than two classes. Cannot belong to more than one class. So if the KK and the L are different, then this sum here is 0. Yes. So it's only non-zero if the G and the G prime belong to the same class. And if they belong to the same class, then KK is equal to L, then this is just equal to H times the number of elements in the class KK, or class L. So if KK equal to L, then we just get H times NK, or NL. Yeah. Okay. That's fine. So now we can do the following. We can write this thing here. I can write this one here.
Excuse me, I still need to solve over K in the top right.
In the top right. In here, you mean? In here?
Yeah.
Let me see. Yes, I have the sums. The point is that I have the sums over the G and the G prime, right? So the point is that if K is not equal to L, so say these two classes are different, then it is 0, yes, because G will never be equal to G prime. Yeah. So then we only need to consider the case when K is equal to L. Okay. So when the K is equal to L, then I will have just have the sum over G prime equals G. Yes. Yeah. So and there are n K elements in the class CK.
Yeah, but you're only summing all the elements
in K. Yeah. Because the L has to be the same, yes? So then I have H times in K, and then I have delta KL. K is not equal to L. Yeah? Good. Now, I can rewrite this part here in this way. G1. So I do kind of similarity transformation. And this is equal to sum index. Once I sum over Q1 here, I'm considering this matrix. I'm just using the definition of the representation. Like this. Now this representation is unitary. You can always assume it to be unitary. So that this guy here is equal to T of delta MI. Reverse the indices. And that is equal to T of minus 1 MI here T1 minus 1 and this is equal to T alpha MI T1. Okay. Step there. We put things back here. We get somewhere in G1 T alpha MI, as I'm using this result here now. G1 T alpha so on and J. Yes, I because I want to use the orthogonality theorem like that. Now I can use this orthogonality theorem for that. It's not sum over G1, that gives me MN and then H alpha and delta IJ and T alpha star and G. Have you with me? So then I can just get rid of this orthogonal delta and then you get significant bit more space here. So let me go here. And then that becomes H upon delta J sum over N T alpha star N T. So this is just retrace. That becomes H alpha delta J star G. So here with me. So here. Okay, so now I can point here. So I put this result. This result back here. Yes, because I'm considering this matrix. Over here, and I realize that I can replace it like that. So let's continue. So then I have sum over G given loss sum over G prime given CL sum over alpha J T alpha J. almost there. Like that, then just using the result. Previous page, like this here. So now I can write take the trace here. Then I get some G, some G prime, some row R, and I get trace. I like this page here. G, so go to just like the same thing. So, the character depends on the class. So it doesn't matter what G is, as long as the G belongs to the class, and then we get the same character. And then I get what do you want to show? Okay. That's the class which G belongs to. And then we go. Okay. There's a second notification.
Any idea way to do divide by one, so should there be on the left hand side?
Okay, so the thing is that I minus some over G, I'm going to do it here. G belongs to CK of our G. Yeah. So that is equal to NK. Chi of CK. Yes, because there are NK elements in this class CK, and the characters are all the same. Is that okay?
Exactly. Yeah.
On the right and the left hand side, we have two NKs.
But when we start the computation, there was an element on the left hand side, just what that is.
Yes, I have a lot. Yes. Check. Yes, we have a lot here.
Mean again. And then that's
that goes away when we use the nominality.
Okay, thank you.
Yes. I think there's a bit of here. Maybe I should have included that here. When I use the nominality theorem, we make it here. Yeah. Right. So this is the thing we want to show. And let me see. Yes, we can navigate here a little bit. If you don't mind. So the last part is actually quite here. Yes. So we want to show that some number of G to the minus 1 G prime is equal to H G prime. So this is exactly follows directly from what we derive before. So let me do this quickly. Again. Finish this. So that's what we have in the beginning. First thing let's show this. Let me use the clarity of the representation. And then we get what do we get here? Yes. So this is equal to sum of ij -1, so then here becomes becomes the unitarity of the representation. That is equal to number of J. So I'm just multiplying this matrix. So I can get it all J minus 1. Right. And then alpha. That is just the matrix. So then you get number of alpha character G minus 1, G prime, and alpha. So that's the thing we want to show. Yes. So this then is equal to that one. Okay. And then we want to have last. So it's the same equation here. Okay, let's go to the last one. This is a easy. So we want to show that there is someone who will given character G is equal to 0 for all the different representations except for the identity. Representation. So this is actually just what are referring from the characters. So we have this emoji, G is equal to PH and so this is the trigonometric. Well, then we choose alcohol to be the position. Then this gives us immediately to this is what it's just for the identity representation. This is just equal to 1. And then we just get G is equal to 0. That's having the yeah, excellent identity representation. Okay, that's easy. Okay. Very common, but I can expand if you like for the last one. Okay, the last question is useful. So don't worry, we expand this. It's very quick. So let's do that. So the thing is that we have a group of DVH, which is a direct product of the DVO and the inversion group. So the inversion group is just a group of inversion and so the unit and the inversion. Then we can immediately write down the table to group I as the elements as easy. And then equals E8 minus small 1 and then 1 minus 1 like this. Now the product group is like that. It's easy to show that we show this character. of this direct group is just the product of the characters of the individual groups. So the character of D4 and the character of I. So then, as we did in the lecture, showed that the reduced representations of the product which is given by the direct representation. So as mentioned before, it's not used to product of two reduced representations, and then we reduce representations of direct product. Later considering direct product, and then they just representations is given by this direct product representations. This reduces. And the character table is easy because of this 48. So I have character table of the D4. So let's just it's convicted. This is the character table of D4. We have to do this multiply this two. And then we get character table. Let's just do D4, and then minus D4. So this is the character table of the direct product. So it's easy if you have a group which is direct product and the intents of direct product consists of groups, then the character table is constructed from the character tables of the individual groups. Okay. Any questions?
Yeah. About this, but I don't know what it is. Is it just a secret group order to?
Yeah. So in the version, there's for example, you go from order to minus not. It's really yeah. It can.
It's isomorphic to C2.
Yes. It's isomorphic to this. Yeah. Or you can think of somewhere like plus minus or something else. That's some kind of version. Yes. I'm sorry.
The table like 10 by 10 in this case.
In this case, it will be 10 by 10. Yes. Because this is a 5 by 5. Yeah. So it's some kind of matrix, but that's necessary to structure this. Can you stop asking if it is a 10 by 10? Can you hear me now? Yes, I hear you.
I'm thinking about this inversion element. This is just the element which we invert in the direct product. So it essentially takes, for example, in the way it takes say C3 to C1.
So yeah. So if you include this subject, so the group D4 is the group of perfect square. Yes. Regions. It's important. This is region square. Is a group which is square of this rotation of this center. Yes. Or you can have a rotation on the diagonal courses, but it's a region. It's a rigid object. Now the rotation cannot be represented by rotation. So the rotation is not a rotation. So it cannot represent inversion by rotation, because inversion that means that you dissolve the object. Bring this point. This is point. So if you make an inversion, and this you dissolve the object. So that then give me this group D4 each. This is D4. So the key point is that the inversion and then rotation, they can move. So that's why we have the definition so then there's this group DH since I recorded the definition group. It's okay. Can you follow what I'm trying to say?
Yeah, I got it.
Yeah.
I'm gonna think about it.
Okay. So the point is it's not one is just they're different. So you cannot place this by teaching. If you just label everything by 1, 2, 3, 4, 5, then this is not a good way because you can rotate whatever. The point is that inversion is not a rotation because it is total objective.
Inversion is not rotation, but essentially all the points when one points at the end of the action should be in the same position as perform 180 rotation or something.
Yes, that's true. But it's more than relay labeling the vertices. So the inversion you cannot write it as a continuous rotation. So it's not a rotation. So you think about the sphere or something. If you make the version, or maybe you can think about this. Maybe think about the coordinate system. X, Y, Z. X, Y. Then you may make a version. Then you can get a different coordinate system. You have a left hand and the right hand coordinate system. So they are not equivalent, they are not the same. Yeah. So then you have my right here, this is new coordinate system inverted is different from the tension. So you have that left hand and the right hand coordinate system. I think it's important later when you do the continuous groups. You can continuous group you can write the independence in terms of 10-20 data. In terms of changes. And you can write them frequency changes of the changes. But not the inversion. You cannot write inversion in terms of increment frequency. Okay, so we are going over a bit, quite a bit. That's fine. So now everybody is happy, and we can stop here. Okay. So have a nice weekend, everybody. Goodbye.